Wonderful. So yes, so my project on model localization and terrain mapping for tabletop war games. So for those of you that aren't familiar with the wonderful, wonderful game that is Warhammer, it is a strategy game played between two players, and you can see sort of an example board on the right. Each player has an army of sort of a couple of inch size miniatures, and units interact with each other using a dice roll. So on the right, you've got sort of like a typical size game, but you know these can scale up to sort of this size game. So this is actually a diorama, but you could, in theory, play a game on this board. I mean, for size of scale, that's my three friends at the back, up the stairs near the top of the board. And so when you've got sort of large boards like this, one of the problems that can occur is the problem of line of sight. So it's crucial to sort of interactions within parts of the game, because what a model can see depends on what it can sort of attack and shoot. And particularly when you've got sort of dense boards like those that you saw earlier, a player getting their eyes down to that model's eye view can be very difficult without disturbing the miniatures on the board, which can cause sort of disagreements and things like that. So this project is based around sort of solving this problem by creating sort of a digital reconstruction of the board. So these are the sort of all the areas that I sort of covered throughout the project, but for today I'm mainly going to focus on these areas just for the sake of sort of time. So first off is sort of the registration tasks so I've created. So I was able to capture some 3D images using sort of an Intel RealSense camera. So it's sort of like a Kinect. So it natively produces these 3D images. So what you can see on the right is two misaligned point clouds. And so what we want to do is we want to take several views and combine them so we've got one sort of 360-degree view and then start to analyze that. So this registration process is about aligning these clouds into a sort of more tighter alignment, as you can see here. And then you can do more detailed sort of like outlier removal and things like that. As you can see, there's sort of like several artifacts that get produced. So the main sort of engine behind this is the iterative closest point algorithm. And so this is an optimization. So you've got two cost functions at the bottom. So if you've got a target point cloud T and a misaligned point cloud S, you want to optimize these cost functions to find the transformation M that will take all the points in S and map it onto T. And so there's two main flavors of this iterative closest point. There's point to point, which is on the left, and point to plane, which is on the right. So point to point, as the name suggests, just merely minimizes distances between points that are believed to be the same point between the two clouds. Whereas points of plane just ensures that points that are thought to be the same between two clouds are merely in the same plane as one another. So this makes use of the estimated normals of each point within the clouds. That's the M that you see there. And then this iterates and re-estimates the correspondences until you get a tighter and tighter alignment. But one of the problems with iterative closest point is that it's very sensitive to the initial alignment. And so you've got to be able to have a way to find this rough initial alignment to have any sort of chance of getting a good reconstruction at the end of it. So in the data sets that I used, I made use of a building and 4 miniatures on a board. And so since I knew that the building would always be present in each of the scenes and is clearly the largest object, it's very easy to identify and then find the corners of the corner of this building. So as you can see, you've sort of got the two planar walls. And so to find the initial alignment, in my case, I created sort of a ransack least squares sort of algorithm that fits two lines that are 90 degrees to one another to a set of points. So as you can see on the left, we've got 4 of the building views if you view from the top down. And you can see that it finds the edges of the building really quite well. And then taking multiple views, applying this algorithm and aligning all these sort of corner points together, you can get sort of the rough initial alignments that you see on the right, which I think you can agree is pretty good, close initial estimate, which works really well to then be tightened up using this iterative closest point that I just mentioned. And so then you can see you get a much more tighter view and you can get a full 360-degree feel for what's going on. And so the overall process, so first of all, we segment to find the building. We apply this ransack fit that I've just described to get this initial alignment. And then we align all the views with one another using this iterative closest point. So now that we've got a more full picture of a tabletop board that we're looking at, we now want to be able to actually like cut out areas and segment them to propose regions of interest for classification, as well as to identify the building initially. So the main segmentation algorithm I use is DBSCAN, or density-based spatial clustering of applications with noise, which is a little bit of a mouthful. But this is a really good clustering algorithm because, first of all, it can find any arbitrary shape cluster, and similarly, it can find any arbitrary an arbitrary number of clusters, which is good because we can have any number of models on the board, and they can be any sort of shape. Really, there's no sort of set shape that they can be. And so this algorithm works really simply. So it's got two parameters. First, you've got a distance r and a minimum number of points p. And so it first of all classifies all the points that you see in blue as the points that have at least p points within a distance r, and that's all the blue points that you see. Then all the yellow points are those that are within r of a blue point. So these form the edge of a cluster. And then finally, you've got the points which don't classify either of these as which you see in red, which is good because it means it can find outliers, as you saw in sort of the previous registration examples, because the cameras can produce sort of several different artifacts. And so how does this actually look like in the process when you apply it? Well, when applied to the scene, as you can see for 4 different layouts, it can really easily identify distinct separate clusters. We do have the problem of in the top right and bottom left cases where there's models in the building where it classifies them all as a single cluster. But otherwise, what you see is a really high quality sort of segmentation. We do still get some artifacts as well. So again, as you can see in the top right example, you see that sort of red line at the edge of the table and things like this. But these can be very easily filtered out using simple height checks. So we know that our models are only going to be between certain height ranges. And similarly, using singular value decomposition, we can find linear regions. And we know that if it's got a singular value close to 0, it's not going to be a model because it's not a fully 3D object in the 3D space. Great, so wonderful. We've got our segmentation now that we can actually begin the classification process. And so to actually classify the models in 3D, I needed a set of reference models to create. So initially on the left, I tried to create them just by cutting out the point clouds that I created and aligning them individually. But as you can see, these point clouds are very, very noisy. And I had trouble for creating them with the smaller miniatures, so I had to find a different way of doing this. But instead, I looked at photogrammetry options. So these are, as you can see, the results are much, much better. So this process works by taking a collection of RGB images, typically 100-ish images per model, evenly spaced around it so you can get that full 360-degree view. With these RGB images, you put it through structure from motion frameworks such as Alice Vision, and this can create a full 3D colored mesh, which, as you can see, these 3D models look really quite detailed. They've got excellent color to them and aren't very noisy. And crucially, they can, because you're using RGB images, they can work for large and small models, respectively. So what do we actually do with these reference models when we're actually classifying? Well, in fact, we actually go back to this iterative closest point algorithm that I spoke about before. So if we take those regions of interest and match it to each of these 4 reference models on the right, we know whichever one has the lowest cost function is the most likely to be matched. But we can take in a couple of extra pieces of information to sort of help our optimizations now that we have a fully aligned scene. So for instance, we know that all the models are going to be on the table, so they're all going to be oriented in a certain direction, which we can easily find by finding the plane of the table. That's a really simple operation. And because there's much less points, we need to use as much information as we can to match this. So taking our 2 cost functions, again, exactly the same as before that we see on the right, but instead constraining our transformation matrix to be a single rotation about the axis of the table, we can get a much quicker alignment process. So, and because again, we've got a much, much smaller number of points compared to the full scene, we can create some least squares solutions, which can be optimized very, very quickly for the classification process. So then matching these against and taking whichever one has the smallest cost function, we classify it as that model respectively. And so the bonuses of this, of doing it like this, is it also gives us the orientation of the model within the scene. And so you can see the classification using both the point-to-plane and point-to-point classification. And so as you can see, the point-to-plane is actually much more consistent. So we get about 80% accuracy here. Obviously, this is a small sample size. But whereas the point-to-point, it generally skews to one of the big models or one of the small models, respectively. And even in that case, as you can see at the bottom, the orientations are out. So the point-to-plane was the one that was focused on for the classification process. And in fact, then that allows us to fully reconstruct our scenes really quite accurately. So I think you'll agree, it's the comparison of the actual image of the scene on the right and the reconstruction on the left are really quite close. Excuse the black splotchiness. This was a bug in my visualization software where it didn't render the textures properly, but you can still make out the shapes, which is the important part. So now we can finally start looking at the problem of line of sight. And so visually, obviously, digitally, we can see what's going on here quite well, but we want to be able to automate this process in a computer just to tell us, can it see or can it not? So this is where I went back to an algorithm from sort of the mid-80s, which is raycasting. It was all used in Wolfenstein 3D, if any of you are aware of that game. And the process works by projecting a series of rays out from an optical center and rendering the object in the 3D space based on what it can hit. And so this is sort of visualized in the bottom figure, as you can see here, where the black lines are sort of obstacles and bits of it are obscured from points that are in front. And so this is great because obviously it mimics how we would naturally perceive objects ourselves, and then it means it can deal with arbitrarily complex shapes again, deal with any sorts of holes and things like that. So I applied this in sort of a planar manner, as you can see on the top, a very sort of rough example on one of the reference models. And you can see how from the front you can see the full model, but when you turn to the side, you can see how it doesn't render parts of the leg and things like that, which are obscured from the hands that are in front of it. And so these are sort of preliminary results as I was getting towards the end of the project, but you can see how this could then be applied to sort of the whole scenes to determine which objects can be viewed based on whether they're even rendered in the first place. So in conclusion, what's been presented in this project is a number of things. So an original initial alignment method that uses least squares optimizations to find sets of corners and points. And then from these combined and registered scenes, taking those regions of interest and applying a much more efficient, constrained ICP to classify the model and create visually accurate digital reconstructions of the board space. The digital reconstruction can then be analyzed and used as an adaptation of raycasting to extend it to continuous lines through 3D space. In terms of further work, ideally, I would like to sort of enhance my classification to be more probabilistic. This obviously has the benefit of being able to deal with miniatures that are the same in terms of rules within the games, but might have different poses depending on how someone has sort of constructed and painted the models. Similarly, to make it more accessible to most players, I would like to move towards RGB image processing. So that's using techniques such as Apple's Measure app, which can find sort of objects in the 3D space and deal with that. And in fact, RGB images are much easier to do sort of convolutional neural network classification and things like that. And then finally, a lot of the work that I've been doing is offline. So I've been doing it largely in sort of Python and similarly related high-level languages. I'd like to sort of look at lower-level implementations, which would obviously give you much more benefit of speed and allow you to do these processes much more online. Great, thank you very much. Is there any questions?